Hey guys, in this video I'm going to talk a little bit about thermal energy. So we've talked a lot about how energy flows through systems. It gives any system an ability to do work. And so it's just an ability, and it flows in and out of systems, and it seems to change form a lot as well. And one of those forms, which we're really familiar with, is a thing we call heat. So we're going to be looking at heat as sort of this idea of flowing of energy through a system, and we're going to look specifically at the molecules in a system. And so this is where the idea of thermal energy comes in. And we also have another concept side by side with that everybody is probably fairly familiar with, and that's called temperature. So these two are sort of related to each other, but a little bit different. And the way that they are related is that they both look at the movement of molecules and the energy in a molecule as it moves, and so, or atom or whatever, just a small particle movement. And you could think of that in terms of gas. For example, if you have let's say we have a balloon here, right? And in that balloon, there's little gas particles, and those gas particles are moving, right, with a certain speed, and they're colliding into each other, and they're hitting, and they have there's many gas particles in there. You know, it might be a helium balloon, so then they're going to be mostly helium particles. But all of these gas particles are going to have linear kinetic energy. They may even be spinning, right? So they might have rotational kinetic energy. They also have potential energy, because if you were to look at the molecules, let's say we had a water molecule, right, in there, right? This water molecule can do some bending, and can actually vibrate. And so actually within it there's potential energy as well. So thermal energy and temperature are going to measure all of this energy that is within gas particles. But thermal energy is specific to just call the total energy with all the particles. So thermal energy is going to be all of the energy. So we're going to be looking at all the kinetic energy, all the potential energy per molecule. So if let's say that this is 1 liter of gas, and if I had another balloon right next to it, which is 2 liters of gas, what's going to happen is this is going to have a higher thermal energy, because it's going to have more particles. They might be the same temperature though. And so what is temperature? So temperature is actually just the average energy per molecule. So when we talk about temperature, this is average energy per molecule. These two might have the exact same temperature. Let's say they're both 25 degrees Celsius, right? So 25 degrees Celsius. If both of these are 25 degrees Celsius, they have the same temperature, because on average, you might have a big one. It's going to be moving slower maybe than a little one. But on average, if you average all these together, their average kinetic energy and their average energy is going to be about the same. The 2 liters and the 1 liter. But if we're going to look at total energies, we have at least twice as much with the 2 liter as we do the 1 liter right here. So that's kind of the main difference between thermal energy and temperature, is the difference between average energy and total energy. So let's talk about sort of some of the things that we observe in the world around us with these moving gas particles. All of you guys would probably be able to tell me what would happen if I added heat, right? Well, if we add heat, a couple things. The temperature might go up, right? The thermal energy would also go up, right? Both of these would go up. Why? Because you're adding energy into the molecules. They're going to move faster. They might have greater potential energy. Now, adding heat or adding temperature to a system doesn't necessarily have to increase the temperature. For example, when you get to the states of matter, so let's say this is an ice cube, right? And so that ice cube is melting. Okay, so that ice cube might be at 0 degrees Celsius, and you can add heat to it, all right? And you would think, okay, well, it's going to start going up from 0 degrees Celsius. It's actually not. The heat or the energy is actually going to go to rearranging the atoms, or the molecules in this case, because it's water, out of their solid form and into their new liquid form, right? So what's going to end up happening is this energy isn't going to go into kinetic energy. It's going to go into rearranging their configuration, I suppose would be the best way to say it, from a solid form into a liquid form, which has a different configuration. And so you'll be adding heat, and the temperature will not go up. So in general, adding temperature or adding heat does increase the temperature, but not always. When you look at states of matter changes, it doesn't. Let's look at some other kind of interesting kind of examples as well. Well, let's think about a thermometer, for example. So what happens in a thermometer? Let's say we have a glass thermometer, and so it's got the little, the little red fluid down here, and then it's got, the line, the tube all the way through it, and it's got the little marks on it. I don't know. It looks more like a really bad baseball bat. But anyways, you can imagine that this is a thermometer if you close your eyes. So what's going to happen, and how does this work? Well, let's say you put this in your mouth. Okay. So here's your teeth. Here's your teeth. Right here, some lips. Okay, we got. Okay, maybe it's an alligator's mouth. Okay, let's say you put this into an alligator's mouth. What's going to happen? Well, as it touches the warmer temperature here, these particles in the mouth here, they're moving faster, right? And they're actually going to collide with the glass on the bottom of the thermometer. And the collision there is actually going to cause these particles to move faster. And when particles move faster, they want to spread out. And so what it does is it increases volume. This is why temperature causes volume to increase, and that's what the thermometer relies on. As the molecules collide right here, it's going to transfer that energy into the molecules right here. They're going to move faster, and they're going to move faster, and that's actually going to cause the liquid in here, which is usually alcohol. In the olden days, it used to be mercury, but now it's red alcohol usually. And that's going to cause that liquid to expand, and as it expands, of course, it's going to climb up that little tube, and it's going to go up with these little marks, and we can read it. And somebody's calibrated that out so that we know that that particular volume means this temperature, right? So what we can tell is that increasing thermal energy and increasing temperature certainly increases volume as well. And that's what a thermometer relies on to measure temperature. There's lots of different kinds of thermometers and lots of different kinds of ways that we do that, like with electronic devices, and sometimes you'll have the electronic things. They have little electrodes that are sensitive to the temperature change, and then that gives you a little bit quicker reading. And so let's also talk about this idea: what's happening when the molecules in, let's say, the molecules in the thermometer are going a little bit slower. These ones hit, right? They're going faster, and then these ones start moving faster. Well, eventually, at some point, which is usually about the amount of time that you're supposed to leave the thermometer in your mouth, what's going to happen is these molecules will be moving about the same speed. And we call that thermal equilibrium. And this hitting of molecules against each other to transfer energy, we call that conduction. So thermal equilibrium would be the point where you would take the thermometer out of your mouth because you realize that we've had enough time where the molecules in the bottom of the thermometer are now going the same, or have the same average kinetic energy as the molecules in your mouth, right? And so that would be what we call thermal equilibrium. So what's going to end up happening at some point is the state of the energy flow between the two objects will be equal when the objects are at the same temperature. And so stuff will always tend to go toward that state of thermal equilibrium. And this process right here, where we're actually physically hitting the molecules against each other, we call that conduction. So in order for conduction to happen, you have to have physical contact of molecules against each other, banging into one another. And literally that's what's happening. Why does the balloon blow up? Well, what's actually happening is these molecules are banging into the sides of the balloon hard enough to hold it open. And so that's why you have to put a certain amount of air in there, because they have to bang into the sides hard enough to hold this balloon open to whatever size. So you blow more in, it's going to get bigger. Why? Because more molecules are banging even harder on the sides. And then what's going to happen when you take the balloon out into the cold air? This happened. My daughter and I, we went and bought a balloon for my wife for her birthday, and as soon as we left the store, it was freezing cold outside. The balloon shriveled up and looked really pitiful. So what happened? Well, all that happened was those molecules in there that were banging nice and hard on the sides, the cold air, right? So we had the cold air out here, was starting to do some thermal equilibrium with the molecules inside that balloon, and they were slowing down. And as those molecules started to slow down, they hit the sides not as hard, not as fast, because they had less kinetic energy. Basically, the balloon would have lost some heat there, right, to the outside world. And so then when those molecules didn't hit the sides, it started to sag and look a little droopy. And so for measuring temperature, we have two different scales. We have what's called the Kelvin scale, and we have the Celsius scale. So Celsius was used to sort of more or less relate with our real world situation, where we have 100 degrees Celsius, and that's boiling point of water, so water is going to boil here. And we have 0 degrees down here, and that's going to be where water freezes, right? And so this is based off of water, so it's a degree measurement of temperature, but Kelvin is the actual unit of measurement. So unit of measurement, because Kelvin isn't based off, when water boils and freezes. Kelvin is based off the actual movement of the particle. So Kelvin actually relates to this. It's the actual average energy per molecule. So it's a unit. So you don't have to say degrees Kelvin, because it's not a degree of this. It actually is this. So Kelvin measures the average kinetic energy, or the average energy of the molecule. And so Kelvin actually starts, freezing point of water would be about 273 degrees Kelvin, right? And every single temperature unit is the same. So if I go up 1 degree Kelvin, I also go up 1 degree Celsius, and so forth. So if I'm going to convert from Celsius to Kelvin, what I have to do, if I'm going from Celsius to Kelvin, I'm going to add 273, because they're 273 degrees off. This one starts at 273, where this one's 0. The easiest way that I remember this is as I'm going up alphabetically. If I'm going from C to K, I see that as going up alphabetically, and so I add 273. And then vice versa, if I'm going from Kelvin back down to Celsius, I would subtract 273. So it's pretty easy to convert back and forth between the two, and you shouldn't have any trouble doing that. But why do we use Celsius? Well, it's more applicable to our real world that we live in. It's kind of a water-based world, and our body temperatures and so forth. And why do we have to have Kelvin? Well, Kelvin is the actual unit of temperature, of the movement of those gas particles. One more thing, there's a very huge range of temperatures in the universe. This is kind of interesting. So if you go to like the center of the sun, right, it's going to be hot. It's going to be really hot. Those things are moving. Those are some fast moving particles, and they're going to be up in the 10 to the 4th, 10 to the 5th degrees. At the center of a nuclear bomb, you might even get up to 10 to the 10th. Degrees Celsius, and so you're going to have all these kind of huge temperature scales, but we don't seem to find a limit to how high it can go. So temperature can seemingly just keep going up and up and up and up and up and up, but we do have a point where it stops, and this is 0. It's not 0 degrees; it's 0 Kelvin. And so at 0 Kelvin, essentially, that is when the particle has no energy, right? And so basically there's no movement, there's no potential energy, nothing. So as far as we know, that's it. Nothing can get as low as that, and we can get things very, very close to that, but not all the way there. So that's kind of an interesting one. And molecules do strange things when they get to about 0 Kelvin and actually start to look more like things look in the quantum world at the quantum level, and do interesting kind of things. But anyways, so that's kind of an interesting factoid on temperature and Kelvin and how it relates to Celsius. So in the next one, what we're going to talk about is calculating heat flow and heat transfer. And so how do we actually measure heat flowing through a system?